Okay, so I'm going to, I don't know, Astro Image J, and it does a lot of things automatically. Uh, so the things I've seen, let me just get something over here, the Conti Exoplanet book thing, guide. So, this thing, which uses Astro Image J. Pretty sure you know what it is. Pretty sure you've gone and looked at it. Okay, it's going to load for a sec. Okay, so you have this, and look at it. Just look at it. It's all this stuff. 34 pages of stuff. Unnecessary. That's my opinion anyway. And also, a lot of stuff is kind of irrelevant, and I disagree with a lot of how he does all this stuff. And it's not necessary, all of this stuff, unless you're in your own observatory and you're doing everything from scratch. So best practices, image scale. Well, you don't have any control over that. The best image scale has been picked by the camera and telescope, so picked by LCO. I'll tell you about selection of comparison stars in a second. Below that detail is not actually necessary, and there's some misleading stuff. Flat filtering is automatically done by LCO. Auto guiding is automatically done. Filter use, well, I've told you about filters. Time synchronization done at LCO. And here's those time systems I was pointing out. So probably this one's the best one to do your final measurements in. But at the moment we're just looking at rough stuff. So you can see all this page here is sort of, apart from this thing, which I'll tell you about in a second, it's kind of irrelevant. Also, selecting, this is wrong. Choice of exposure time I've talked to you about. You can set up your own. Who cares about file directories? So, like, I have this problem with most amateurs writing stuff for people to use. Like, this is all relevant. This should not make any difference. You don't need to do all this. So, we're down to page 11, and none of this is actually useful yet. Alright, you don't need to do that. None of that. And I wouldn't do it this way. So, I don't know Dennis. People seem to like him, from what I've heard. But, it's not a beginner's guide. So what I would recommend, there's two sections in Our Solar Siblings that will help you out. And there's an automated way that this Astro Image Day does this automatic thing, which is all well and good, but the students aren't going to learn anything by using it. Like, look at that. Look at it. What? What is that? I don't know. Okay, this is actually probably useful. This probably calculates BJD for you. So I'm just being nasty here for no apparent reason. But this one is probably not very useful. And confusing. Okay, I'm just picking this and being purposely nasty. But not really nasty. This is a bit too much information. So Astro Image J is good, sure. But it actually doesn't do the most accurate measurements you can do. So that is a important point. But at the same time, it also doesn't do the most accurate or the most sort of educational way of doing things. Because you'll get a magical light curve out the end and it'll be done automatically. But will the students actually really quite understand what's going on? I'm not too sure about that. Okay, so, and yeah, this shouldn't happen. Okay, anyway, the rest of it, a lot of it's about exoplanets, which you're not doing, but you want to. Okay, come on, all over the place at the moment. So there's two parts of Solar Siblings that do photometry in the main kind of class section. So I'll just show you where they both are. So in class 2, towards the end, let me just see here. Is it this one or is it the next one? Back up. Okay, so here we have part of the Australian curriculum, and probably part of American curriculum is Hubble's law and all that kind of stuff. And we picked supernova because we have, well, the USA has as well, a Nobel Prize winner who, ours is Brian Schmidt, but you have the other two. What's their face and what's his name? Reese and Perlmutter. But we used supernova to kind of measure the distance to this nearby galaxy, and we do that by making a light curve, coincidentally enough. That's what I'm talking about. So if we have a look in documents, and we have a look here, supernova sheet background edition. So this is geared up to do a supernova light curve, and I was going to make a more generic version, but for the moment this will do. So here we have, your file name, filter and stuff. So you'd probably do one of these for each of the filters. So if we have a variable, comparison, check, and background. So if you can see I've been doing diagrams for other people, very entertaining. If we have a look at some of your images, which for some reason are only slowly coming into my computer, but they're coming down on the other computers, so I've got to check out what's going on. But here we have an image, and here we have the star. Okay, and we want three things. Okay, new screen here. Whoa, that's very intriguing. Okay, so you have 3 stars, so you have 1 star, which is your variable, and another star, which is comparison, another star, which is your check. So variable, whoa, it's tiny. Comp and check. Okay, so you want these 3 stars are your basic 3 stars to do a light curve. So the variable star is the one that's changing, and so it's going up and down. Whoop. So it's going like that. And the light curve of the comparison star should be flat. And the the check star should also be flat. So if you plot the brightness over time, you have the variable going like this, and the comparison flat and the check flat. So you don't know what I'm talking about yet, but basically if you look at any image, and then you look at, and say, I'm using an R1, this one is, about half a day apart or something. If you look at 2 images, and we'll zoom in here, you'll see they're quite different quality, yeah, and the background's a bit different. Let's have there's all sorts of different stuff going on. These are 2 different cameras. This is KB88 and this is KB27. You can see the background has different noise profiles and such things. So yeah, and so one light here, I assume this is Siding Springs because the image is, no, Haleakala. Okay, what's this one? Siding Springs, Tenerife. Okay, wrong twice in a row. What's the odds of that? We can figure that out. But So you can see that between, well, especially between two observatories, even though they've got similar cameras, they're going to have different, quality of image. So you're not going to be able to measure this star just directly off there and then compare it to this star directly off this image. And also depending on, okay, so you have, if there's more moon in the sky, the background will be brighter. If there's more cloud in the sky, all of the stars in the image will be dimmer. Like all of them will be dimmer. Uh, and so the amount of dust and stuff in the atmosphere and the temperature and all sorts of stuff, even over the course of a night, means that you could not just draw a circle around this and measure it, and draw a circle around that and measure it, and it be all hunky-dory and comparable. But let's just assume we're going to use this as our comparison star. But we can say that this star, the difference between the variable star and this star will be the same, regardless of if there's more cloud in this one or less cloud in this one. Both of these stars will be affected similarly by the amount of cloud, or there's more light in this from the moon than that one, but the difference between the two should be the same in every single image. So the difference in brightness, well, because this is variable, that's not true, but we're going to say this is flat all the time, yeah, and we're going to use this star as our kind of 0 point to measure how bright and dim this star is getting, right? But then you have another problem, which is, how do you know that this one isn't variable? So that's why you have I'm losing myself here, a check star, right? So you find two stars in the field. I tell you how to do it, and in your spreadsheet you can make your own, but I've already made this. You measure the variable, then you measure the comparison star, which you assume is flat, and then the check star, which you hope is flat. So I don't have any data in here, so let me go and get my teacher's cheat spreadsheet. So you can see that here you can put the date, time, hours, and seconds, but maybe I should have I'll put a column in there for MJD as well. Sorry, just had a phone call there for a sec. It threw me off my game. Where was I? Oh yeah, I'm going to put an MJD column in there, and that would be good anyway. So here we go. Back to the teacher's cheat sheet. So you can see, if you have a look, this is for let's just assume it's for this thing, and that's the variable, that's the comparison, and that's the check. It's completely not true, but I'm just using it to explain what's going on here. Yeah. So if we look through different images, and you assume that this star here is a non-variable star, and this star here is a non-variable star, then their light should be the same in each image, right? But that's not the case. You put a circle around this in one image, and then you put a circle around it in the next image, and you get different amounts of counts. Even though I actually already know before, a priori, that this star is constant, you can see it's varying, maybe 3 times, from about 1,000 to 3,000. And that's because different nights is looking through different amounts of cloud, so you're looking straight up or you're looking across. You can see that the difference, because this check star is also stable, the sort of difference between if this is higher, then that is higher, that's higher, that's higher, that's higher, still that's higher. If we go back down, that's so. Let me just, if you kind of look at the ratio between these two things, that should be about 2-ish. Ooh. There's a bit of variation. That variation is also due to the low counts in this particular image. Remember, we should be getting tens of thousands, hundreds of thousands of counts, but we're actually looking at something dim here, so that kind of variation I'm seeing there is just due to natural Poisson noise stuff. So the variation will be square root of that in many counts. Anyway, getting beside myself, I am trying to show you an example, not going to nitty gritty. You see, that's vaguely true. This goes up, that also goes up. They're about the similar. Variable, however, changes a lot more. So there's no kind of correlation between here and there. The variable goes up. Ooh, well, yeah, see? It gets really bright at some points, and then dimmer at others. So if we come over here, it does the comparison now. I'll show you in a sec. Here's a supernova light curve. So if we have a look at the comparison and the check star over time, because they're dim, this is a bit noisy, but it should be kind of flat if you draw a line through there. It's not very convincing here, but if you saw the images, actually I'll just show you just for interest's sake. If you saw the quality of the images, you would know. See, look how, oh, it's not so bad, but they're pretty cruddy images. You can't actually see the galaxy very well. And the supernova and stuff is some of these dim stars. So it should usually be flat, but they didn't get enough counts. But you have to work with what you've got. But then, if you know the comparison of the, if you know the magnitude of the comparison star, if you know what this magnitude is meant to be, what its actual true brightness is, and then you know the difference between the variable and the comparison, which is here, you see, so this is in magnitudes, and there's some wonderful calculations going on over to the right here, which is a secret magical wonderland if you want to know what's going on there. But for the initial parts of this, you could pretend that doesn't exist, so nobody gets confused, which is what I do. So just these counts get converted into magnitude, so it compares these two and gets the difference in magnitudes. We can certainly go over to the right and pull those equations apart, and they're not really that hard if people know logs. But one thing at a time. Let's get the data out. So it's calculating all that, and because we know the difference between the variable star and the comparison, because that's what this is, and we know the magnitude of the comparison star, we can just add this value to that value, so, and then get the actual magnitude of the star. Yeah, sounds good. So yeah, so here we see that it's going, the magnitudes are changing dramatically. There's 4s, 3s, 2s, 1s. If we did this for comparison minus check, it'll be minus 0 point something, and it'll stay essentially, that value will fluctuate like you see over here. Yeah, oh yeah, 0 0.6, then 0 0.8. But here you see the variable, and it's changing over 6 or 7 magnitudes range. Yeah, so to do it manually, which is probably the way you would like to learn the thing, get the variable, measure that, measure comparison, measure the check. Okay, this section here I'll come back to, but you could probably leave this as 0. But if you go through, and you've got to make sure everyone uses the same aperture size, you could go through and measure the variable comparison check for each of the images, and just do it in one filter. Okay, so the problem I have now is the problem I had when I was talking about this and Astro Image J and all this stuff, right? Astro Image J won't give you the best results for any given uh, measurement. Like, you can use Astro Image J to measure it, but it won't be as high a signal to noise. It's not the best aperture photometry tool. The actual best aperture photometry tool is actually called aperture photometry tool. And it's a bit uglier, but it allows you to do things much more precisely and measure things with a higher signal to noise. So I'm just trying to think through, like, what would be the best way to do this, because aperture photometry tool, it's quite confusing to use sometimes. That's the best aperture photometry tool, but then you also have the Our Solar Siblings pipeline. Just do too much stuff. Don't know where anything is anymore. My wordy. Okay, sorry. It's getting a bit rough. So we have this pipeline that automatically goes through and does all this stuff. And here's where your images turn up in your lovely Dropbox. But then it also automatically does the photometry. So the thing we need to think about is the photometry that comes out automatically from this pipeline is way better than you can do with Astro Image J. And Deophot, which you can't use unless you use a Linux command line because it looks like that, is 5 to 10 times better than aperture photometry tool. So you got Astro Image J, which is okay, and then aperture photometry tool you get signal to noise about 2 or 3 times better, and Deophot gets it even better. So if we got them to do all the stuff in Astro Image J, where it's kind of easy, then the data, the results aren't as good. They're not as scientifically useful as if they got to use Deophot. But if you use Deophot, so if we follow this line along here, photometry catalogs for each image for each method generated. If we go into your folder, FOT. So here's all the different methods, and Deo is the best. See, for each image you have a file, and each file looks like this. Has RA, dec, pixel X, pixel Y, counts measured, and counts error in counts. Now this has automatically already been done, and it is 10 times better than what the students can do manually. So it's an eternal question I always have, is if this is so much better and it's done automatically without any effort, then why get the student to do it manually? Of course, the real answer is if you do it manually, then you understand what's going on. So if you've done it manually, then you know what all these numbers mean. So obviously, you have to do it manually at some point. But for the final go around, we probably want to use these numbers in here. But we're a bit far away from that yet, and I'm sort of thinking out loud for your project. I would think that to see how your light curve's going and to learn about photometry, I would use Astro Image J just to plot and see what parts of the light curve you have. So if we you might find that you've already covered the light curve pretty well, and so it doesn't really matter, or you're not too sure. So for the students to learn what's going on, we'll just have a look in one of the bands, the V band perhaps, and just keep on as the V keeps on coming in. We'll keep on adding the points to an Excel sheet. Yeah, and just keep track as we're going along. But in the final analysis, we'll have to use the counts and error from this more chaotic looking sheet. Okay, so I've opened up Astro Image J and I've just opened up an RI Lyrae image. So here is our variable RI Lyrae. So take a measurement of that. And so there's the source minus sky. So we'll chuck that in there, 561,194. Then say our comparison is here. We'll take a measurement of that. I'll go through. Oh, that's nice. Nice. It kind of does the table. Does it in a table for you. So it could go comparison, variable comparison check. So these are the values, sort of values we actually want to see. The values after the decimal point is really even 1 decimal point isn't worth that much, but maybe go to 2. There's no point writing out all the small numbers, but your students will think it's really accurate. Secretly, it won't make any difference. So look at that signal to noise. That's amazing. Ooh, peak's pretty high. But anyway, so we have that one, and then let's open in this window. Let's open some other image. Ooh, that's pretty cool. 1, 2, 3. So now we've got this. See how we've got a much brighter background. I think there's some kind of cloudiness happening, and you see that the counts have come down significantly. But you can see they've come down significantly, but in a similar ratio. I probably got these in the wrong way. He probably caught me doing that already. So yeah, got some values down here yet? No, because it won't give me any values until I put the date in there. So the version I'm going to send you is going to have another column for MJD, okay, and then it'll work. But basically that's the idea. So do that again. Open another image. Hopefully it'll be another instructee image that. Whoa! I have something. Oh, this is a super duper high exposure. So this will be overexposed, but just for fun. So here we go. Signal to noise 2000. This is certainly overexposed. The peak is 130,000. That is certainly saturated. 60,000 is dangerous. So here we have 4 million or something. So this is an overexposed image, and this is the danger. So you might have all of this high signal to noise, but this value will probably be, you'll have to reject that. And you put that in there, it'll be the same ratios. Let's try that out actually. Where am I again? Okay. 489,704 330,368. Have I done it again? I have done it again. 438, 5.8. So if we, this is always going to be different. just to play around with it, I'm just going to go, here's that, divided by that. So these should be 4-ish. What? What did I do? Let's type these in again. Something weird's going on with my brain. I need to go and get it checked out. Then we have this 12373026. Am I just looking at? I'm going mad. This is another reason why it's great to automate this, because it actually screws with your head trying to make sure you have the right values in the right spot. But you can see this comparison and the check are roughly in the same proportion to each other, even though this is more than 10 times exposure time. This image has cloud in it, and this image is probably just nice. It is nice, because the variables got in the nice range that I was talking about. So as your images come in, you could start putting them in. You could have like a little Google spreadsheet where you just have this section. People can put their own values in there. I'll get it so it plots on here as you go along, and that's about it. So I'll make a version of the spreadsheet that'll be very useful to you. That's the general principle of doing it manually. And then I should get a good idea what's going on. There are stuff in... Sorry, this video is a bit of a schmozzle. There's stuff in PowerPoint's Supernova Big Bang PowerPoint that you should be able to steal. So it's talking about the MM101. There's saying in Macaulay, but it's probably useful. What's probably more useful is the one you probably already know about, which is the major photometry thing in our solar siblings, which is class 2, which has all of that stuff again. Yeah, and it also has what happens when you do color. So in this one they do a color magnitude diagram. Yeah, but you get the gist. Instructions for different software, but you know, you can plagiarize something from there. So, sorry, this has been a bit of a schmozzle video. I'm just trying to give you an idea of where we would go, in that we would actually, in the final rundown, use the values from here, and I have some software that will automatically get the values out for them, which you don't need to tell the students about. You could get them to take them out manually, but we have software that goes through and picks out the variable, the comparison, the check, and whatever else other stars they might need automatically. So I'd say stick to one filter, probably the V filter. Keep on measuring the stars as they come, the images as they come in. Start getting some dots on the graph, and they'll just look all over the place. And then once you have some measurements done, I'll tell you how to use Paranzo, which is actually quite easy to use. I pretty much showed you before, but just to illustrate how easy it is, he says, making it look harder than he intended. What? Yes. I've made it look harder than I should have done. Sorry. Where's it all gone? Okay, that'll do. Whew. That's getting really boring. Voila. Okay, there's a very kind of rough light curve. So once you get the data out like this, we can put it in Paranzo and get the light curve out. This has dragged on for too long. I'll be recommending you watch this very quickly, and you'll probably have lots of questions at the end. So